This is video number 3 for the electrochemistry class, September 28, 2015. We explained the interface between a metal and a semiconductor, a metal and electrolyte, and we saw that the formation of the double layer charge is kind of taking over of the energy difference between the electrode and electrolyte. And that's the very basic system. However, there are possibilities that the material, the redox material in the electrolyte would face some sort of the transition. And here we are going to review that part to see that what exactly happens in terms of the reaction and how we can relate that to some, energy structure for a metal electrolyte. So again, I'm emphasizing that at this time we are looking at the metal electrolyte reaction or interface, and then after that we'll look at the semiconducting electrolyte interface. So what you should remember is that when you're talking about I better to write this on the board maybe. So what we have here is that let's say that we have Fe3 plus electron is giving us Fe2 plus. So this is called I hope that maybe I have to write a little bit harder in the font to be seen. So we have Fe3 plus an electron would give us Fe2 plus. So when we have such a redox reaction, this is the oxidated, it's the iron in the oxidated state, and in the reduced form it's the Fe2 plus. So but usually in an electrolyte, if you have such a thing, the reaction could be reversible, so meaning that some of the reduced form of the iron would get to the oxidized form too. But the reaction reaches to an equilibrium when the rate of the reduction is the same as the rate of the oxidation. And as long as we have this sort of the equilibrium condition, we can have both Fe3 plus and Fe2 plus in the electrolyte, and each of them would have a certain concentration. And when we have such a reversible reaction, we can assign an electrochemical potential to the reaction. And as we learned before, the potential that we have is kind of presenting the energy in the system. So it's the potential of the reaction is expressed by unit of volt, whereas the energy of the system is presented by electron volt if we use the unit from the semiconducting technology. So as long as we are assigning potential to this reaction as a redox reaction, it means that this system possesses an energy. However, we have to be careful that we are talking about two different entities that each by itself could present a state in the energy system. So when we have such a system, practically what we can say is that iron in the oxidized state may have the energy level like this, whereas the iron in the reduced form has a different energy level like this. And what we call it as the redox potential is the average of this redox potential. Is the average between these two levels of the energy. And but remember that when we are talking about Fe3 plus, it is not really a single ion that we are talking about. We are talking about a bunch of the ions in the form of Fe3 plus, and because of the thermal energy that they possess, the distribution of the ions in the oxidized form in energy is presented by a sort of the Gaussian distribution. Same as that for in the reduced form. So practically what we have is that we have a bunch of Fe3 plus, which in the energy, this is the energy level or the potential level. It's the distribution of these ions in the energy is mimicking a Gaussian distribution, and distribution of the reduced form of the ions are mimicking another Gaussian distribution. So the point that's the average of these two is showing us the average potential, which presents the potential for the redox reaction. So if you remember what we had before was that the potential of the reaction is really depend on the concentration of the ions. So in a Nernst equation was saying that E is equal E naught plus RT over NF or ZF times Ln of the concentration of oxidant over concentration of the reduced form. I apologize for the notes on the board, but I hope that this part is seen. So this is the Nernst equation. So it is practically telling us that in a case that the concentration of oxidant and reduced form are equal, we can just have a potential that's kind of the average here. But if we increase the concentration of oxidant form, then the potential would be higher, and if the concentration of the reduced form is more than concentration of oxidant form, then the potential would be less than this. So we want to see that how this can be kind of shown in a graph like that. So I'm hoping that the diagram here would be more clear. So first of all, as I explained, this is the case that we have. We call this level of the energy as the redox potential for the reaction, while we know that the distribution of the oxidized and then the reduced form is mimicking a Gaussian form. So if we, for any reason, we increase the concentration of the reduced form and decrease the concentration of oxidants form, so meaning that balanced reaction would be pushed to one side to generate more reduced form of the material than oxidized, then as you can see, the average would not be the same as it used to be. It moves to a little bit higher level. And that's the reason that Nernst equation is showing that the potential of the reaction with the concentration of reduced and the oxidized form of the material, if they are not the same, would be different than the standard potential they get. So this is actually giving us a hint that the solution can, the electrolyte solution can match up the energy if we can play with the concentration of the reduced and oxidized form of the material. So the equation that you see back there is the Nernst equation. It's in a different form because this time it's about the energy, not about the voltage. So therefore, instead of E and E naught, it's a mu and mu naught is used, and instead of the RT over NF, it's just a KT, which KT at room temperature is about 25.9 millielectron volt. So what we can say is that here is the interface between a metal and an electrolyte. I already mentioned that the very first thing that happens is that if you insert a metal in the electrolyte and the energy of these two are not matched, a double layer charge would be formed to kind of
shield the electric field and match up the potentials. However, that's for the case that we physically move the ions toward the surface. If that motion of the ions to the surface bring the ions so close to the electrode that the electrode can participate in the redox reaction, then some imbalance of the redox reaction can take place, and therefore we get a different level of the energy. I'm going to stop the video again and go for the last video after this.